Hello and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 5, Lesson 3 on slope and similarity. Alright, so today we're going to get into one of the most important ideas in all of math, and that's the idea of a slope of a line. How steep it is, right? I mean, if you've ever been riding a bike and you have to go up a hill or something and you got to work pretty hard to do it, it's like, wow, this hill's got quite a big slope, right? Slope is sort of synonymous in math with steepness. So we're going to really start to look at slope today, and we're going to see a little bit of a tie-in between slope and similarity. So let's jump right into it and start taking a look at things. All right, let me get rid of that. You won't need your calculators today particularly, but if you want to have them out, that's fine too. Let's take a look at exercise number 1. Let a proportional relationship between x and y exist such that the point 3, 2 lies on its graph. Letter A asks us, what is the equation of this relationship? Solve this for the variable y in terms of x. All right, so let's just recall what this all means and how we do it, right? If we say that there's a proportional relationship between x and y, what that means is that when we divide one of them by the other one, we will always get the same value. Now, we typically, when we're talking about x and y, we typically always go with y divided by x and not x divided by y, but to be clear, it really doesn't make much of a difference. So let's actually kind of go through letter A together. So I can say that y divided by x must always equal 2 divided by 3. And I can say that because the point 3, 2 lies on the line. Now I can rearrange this and say y is equal to 2/3 times x. And the reason I'm doing that is because the problem asks me to solve for the variable y, which means y's got to be all by itself. It's got to be isolated on the left-hand side of the equation. And now what's great about this equation is that if I give you a value of x, right, you can then produce the value of y. So let's take a look at that in letter B. Give the values of y for each of the following values of x based on your equation in A. Show the substitution. All right, well, let's do the first two together and then we'll have you do the last one on your own. The first one is so simple. You know, I almost don't need the equation for it. When x is equal to 0, what's y equal to? Well, in that case, right, I'll use the equation, although it's a little silly to use the equation. Y will be 2/3 times 0. And 0 has this fantastic property that when you multiply any number by 0, you simply get 0. So when x is equal to 0, y is equal to 0. And anytime we have a proportional relationship, the point 0, 0 lies on that relationship. Because remember, proportional relationships are always y equals a number times x. So if x is 0, it don't matter what the number is, y is also going to be 0. Now here, in the second part, we have a little more work to do when x is 6. So when x is 6, y will be 2/3 times 6. Little fraction work here, 3 goes into 6 2 times 2 is 4. So y is equal to 4. All right. What I'd like you to do is really quickly figure out what y is going to be equal to when x is equal to 9. All right. Well, again, pretty easy. When x is equal to 9, y is going to be 2/3 times x, so 2/3 times 9. Again, 1/3 times 9 is 3, and then 2 times 3 is 6. All right, great. Now, let's take a look at letter C, okay? It says, plot these x, y points on the graph, connect with a line. All right, so let's do it. I've already got the point 3, 2 graphed. Obviously, the point 0, 0 is quite easy. It's right there. Let me just move up a little bit. Then we're going to have the point 6, 4. Let me move my ruler out of the way. 6, 4 is going to be right there. And then I have 9, 6. Now, what we're going to see in this situation is that all of these points lie on a nice straight line. Okay, let me get my ruler out of here. Maybe put a little arrow there. The line actually also extends in the other direction, but we're going to deal with negative numbers in a future lesson. So we're just sticking over here in what's known as the first quadrant for right now. But a nice straight line. Now, letter D. This is very, very important, letter D. Let's take a look at it. State the ratio of the increase in y to the increase in x for this proportional relationship. Illustrate on the graph. All right. So this is really, really important. Let's actually take a look at the graph, and let's kind of focus maybe on, this point and this point, right? And think to ourselves, if we were moving from this point to this point, how would we do it? Well, if we had to move along the grid lines, right, what we would do is we would move 3 units to the right and we would move 2 units up. And likewise, here we would move 3 units to the right and we would move 2 units up. You can even start from here as well. 3 units to the right, 2 units up. So in other words, what we know is that when x increases by 3, y will increase by 2. And that's exactly right. That's exactly what this number is telling us. And we talked about this a couple lessons ago, right? When we've got the constant of proportionality written in fraction form, then the denominator, the number on the bottom, right, tells you the increase in x, and the numerator, the number on top, tells you the increase in y. You can see that a little bit better actually when the equation's in this form, right? The x goes with 3 and the y goes with the 2. But really what those 2 and 3 are telling you are increases. For every 3 units of increase in x, 1, 2, 3, we're going to increase y by 2, and then increase x by 3, and increase y by 2. Okay? Now again, as I mentioned, this gets into an amazingly important idea, so let's kind of get into it right now. In a proportional relationship, the constant of proportionality is also known as the slope of the line. In fraction form, it represents the ratio of the change in y to the change in x. So that 2/3, that's that thing I mentioned right at the beginning of the lesson, the slope of the line, how steep it is. So 3 units of change in x correspond to 2 units of change in y, and what that kind of allows you to do with a line is if you know a point on the line, you could then get other points on the line by literally just following the slope. Oh, I'm gonna go 3 units to the right, 2 units up, 3 units to the right, 2 units up. You could do the y first. You could say, I'm gonna go 2 units up, 3 units to the right, 2 units up, 3 units to the right. Most of the time when I think though about the relationship, it's always how is y changing in relationship to a change in x? So as we move to the right by a certain number of units, in this case 3, how many units up do we move, in this case 2? All right? The slope of the line. So important. The number that's multiplying the x variable in this proportional relationship. So let's get a little workout on that in exercise number 2. Graph each of the following using its slope, label each with its equation. All right, now again, I want to be very clear. Every one of these is an equation of a proportional relationship, which means every one of them is going to go through the point 0, 0. It's going to go through the origin. All right? Now, the question is, what other points does it go through? Well, let's take a look at letter A, right? What letter A tells us is that for every 3 units of increase in x, we have 1 unit increase in y. I'm not going to keep writing all of that out eventually, otherwise, quite frankly, we'd run out of space. But look at what we can do with that now. Let's go to the graph, right? I can now, on my graph, go 3 units to the right and 1 unit up. And here's another point that will lie on that graph. Then I can go 3 units to the right and 1 unit up, another point. 3 units to the right, 1 unit up, another point. And now I can take my ruler, I can connect them with a nice straight line. Now I can get my ruler out of here. And that is y equals 1/3 times x. Barely fit it on there, but it's there. All right? And again, it makes graphing these kind of things exceptionally easy. If I have y equals 3/2 times x, let me introduce a little bit of notation that we saw a couple lessons ago, what's called the delta notation, the change in notation. So if I want to talk about the change in x, I can just say the change in x is equal to 2. So that little triangle symbol, the Greek letter delta, stands for the phrase change in. So that doesn't look like the word in. Let me change that. The change in. So the change in x is 2. The change in y is 3. Or apparently 4. No, the change in y is 3. So what can I now do? Again, remember this line is going to go through the origin. So I can now go 2 units to the right, 3 units up. 2 units to the right, 3 units up. Let's go ahead and do that. 2 units to the right, 3 units up. I'm going to stop drawing the arrows only because it could get a little bit messy on here if I keep drawing them. But I keep going 2 to the right and 3 up. For every 2 units of increase in x, 3 units of increase in y, and I get this line. Anytime we have 2 or more lines graphed on a grid, we should always label them with their equations. Y equals 3/2 times x. Now let's look at one that's a little bit different. Y equals 4 times x. That one's a little bit trickier because the slope, which is equal to 4, right, isn't written as a fraction. Anytime you have a whole number that's not written as a fraction, you can always write it as a fraction by putting it over 1. In other words, 4 can be written as 4 divided by 1, right? So the slope is 4 divided by 1, which means for every 1 unit of increase in x, we're going to have 4 units of increase in y. This is going to be a very steep line. 1 unit to the right, 4 units up. 1 unit to the right, 4 units up. Right? So the larger the slope, the larger the actual number, whether that number is 3/2, 1/3, 4, 3/4 in the last example, right? Look at how steep that line is compared to the other ones. And that's because the number 4 is so much bigger than the number 1/3 or the number 3/2 or the number 3/4, etc. Right? The bigger that number is, the steeper the line will be. If we had like y equals 100x, it would be like shooting up to the moon, you know? I mean, for every 1 unit to the right, you'd go 100 units up. And the last one, y equals 3/4 x, follows a similar pattern. Why don't you pause the video and see if you can squeeze that line in on our grid. All right, in this case again, right, we've got the change in x will be 4. The change in y is 3. So starting at the origin, I'm going to go 4 units to the right and 3 units up. 4 units to the right and 3 units up. I'm only going to be able to fit those 2 additional points on there besides the origin. That's enough. Honestly, for a line, you actually only need 2 points to be able to really draw it, but it's good to have a bunch. Good to have a bunch. All right. I'll put maybe my label right here, y equals 3/4 x. That's not a bad place to label them, right on the grid if you've got the room. Okay. So again, before we move on, just to be very clear, right? If I've got an equation of the form y equals a number times x, then that number is the slope. And that slope, especially when written in fraction form, the denominator will tell us how many units of increase we have in x, and the numerator, the number on the top, will tell us how many units of increase we have in y. And yes, eventually we'll have lines that decrease, eventually we'll have lines that don't go through the origin, and we're going to be getting to all of those in the next couple lessons. For now, though, I want to explore something a little bit deeper, right? Why do straight lines through the origin have equations that look like this? Y equals some number times x. By the way, oftentimes, we've used k to represent the constant of proportionality. We're going to start to segue over to using the letter m. For some reason, when we talk about just graphing lines, all right, the slope is almost always represented by the letter m. Why is that? I actually don't really know. But I like it in the sense that m I think of standing for movement, the movement of the line, right? So how do you move from one point to another on the line? Oh, I go 4 units to the right and 3 units up. Or I go 1 unit to the right and 4 units up, or 3 units to the right and 1 unit up, whatever that fraction is that the slope represents. But you're going to start seeing me more and more use m for slope, so I guess get used to it? I don't know. You will get used to it, I promise. All right, so let's really get into why it is that I know that if I have a line that goes through the origin, right, then its equation must look like y equals a number times x. Let's take a look in exercise 3. In the picture at the right, a straight line passes through the origin at A and through point C at 4, 3. It also passes through point E at x, y. Vertical lines are drawn from C and E down to the x-axis to points B and D. All right, great. So let's talk about this setup, because what we're doing now is actually kind of a little bit sophisticated. We are going to come up with the equation of this line, not based on work that we've just been doing recently, but based on similar triangles, okay? So this is kind of cool. So to begin with, letter A. What types of angles are angle ABC and ADE? Mark these on the diagram. All right, so you should be able to figure this out. Now, don't forget that this line, CB or BC, and this line segment, DE, are both vertical lines, right? Very important. They're vertical. It's not like I took this thing and went shh, and like shh. These things are vertical lines, all right? So, based on that, pause the video now, tell me what kind of angles those two angles are, and then mark them on the diagram. All right, well, the plain fact is, if this line segment and this line segment are vertical, and of course we know that the x-axis is horizontal, then angle ABC, which is this angle, and angle ADE, which is this angle, must both be right angles. They have to. Vertical and horizontal lines are perpendicular to each other, so these are both right angles. Well, let's throw them in there. We got a right angle there, we've got a right angle there. Fantastic. All right, let's keep going. Just bring this up a little bit. Letter B. Explain why angle ACB and angle AED must be congruent. Hint, think about parallel lines. So let's again make sure that we get where those angles are. Angle ACB, which is this angle, and angle AED, which is this angle, I claim are congruent. Why do those angles have to be congruent? Let's actually draw them in really quick as congruent. Let's put like an arc there and an arc there. Why would those angles have to be congruent? Pause the video now and see if you can remember some work that we did with parallel lines. Well, these two angles, right? These two angles are corresponding angles that have been created by the parallel line BC and DE, right? And if you recall our work with parallel lines, there were lots of different angles that were congruent. Alternate interior, corresponding, alternate exterior, vertical angles, actually those had nothing to do with parallel lines. But the point was there were lots of different types of angles that were created with parallel lines where they were congruent, right? In this case, these two angles are congruent because they're corresponding angles created by parallel lines. So let's get that down. They are corresponding angles created by parallel lines. Awesome. So now, let's take a look at letter C. I want to keep the diagram up there as much as I can. Letter C. What does the information from A and B tell you about triangle ABC and triangle ADE? draw them separately below and label with congruent angle pairs and dimensions. All right, so in other words, I want to think about triangle ABC and triangle ADE. And actually, let's again kind of draw them down here. We don't have to quite draw them to scale, but while we've got the diagram still in the picture, here's going to be triangle ABC, and I'm going to put those two corresponding angles in there and with dimensions. I know that's 4 and I know that's 3. And then the larger triangle, all right, let me get that thing in here, and that's ADE. And all I know about that is that this distance is x and this distance is y, right? That's the best I can kind of label this one, all right? But what do we know about these two triangles? Think back to our work in the last couple units. What can you say about them? Well, you can say that they're similar, right? And you can say that they're similar because we've got two angles of this triangle congruent to two angles of that triangle. And remember, we spent a lesson a couple units ago on similar triangles and what made them similar, right? And we had this idea that if you had two angles of one triangle congruent to two angles of another triangle, then the two triangles had to be similar, all right? So now I'm going to kind of bring this up out of the way, and I'm going to say they must be similar triangles based on the angle theorem. All right, or criteria. I think we called it a criteria in this course. In high school geometry, you might call it a theorem, but in here we'll call it a criterion, because of course that makes a lot more sense than theorem, right? So these two triangles are similar. You remember this symbol for similarity? This triangle is similar to that one. So let's take a look at letter D now. What can you now say the ratio y divided by x will always be equal to for triangle ADE, no matter how large or small? All right, so again, this is important. No matter how big or small this triangle is, in fact, it could even be smaller than this, it could be teeny tiny minuscule, or it could absolutely be huge, what can I say that y divided by x must be equal to? Well, because the two triangles are similar, right, we can say y divided by x must be equal to 3 divided by 4. All right, so y divided by x must be equal to 3 divided by 4. Remember that when we worked with similar triangles, we would say, the ratio of relatively positioned sides must be proportional. This side divided by this side must be equal to that side divided by that side. And that now lets us easily answer question E, write an equation for y in terms of x, and what is the slope of this line? So this is a piece of cake, right? I can now take this equation, which is something that we've been kind of working with lately, and I can multiply both sides by x. So y will be 3/4 times x. With the slope, I'm going to use the letter m right now, being 3/4. Right? Oh, I got to extend the page there. Awesome. Last part of this question. Another point lies on this line with coordinates of 20, k. What is the value of k? All right. See if you can figure out what the value of k must be. Oh, it's actually pretty simple. And the reason it's pretty simple is that really, the whole point of an equation like this, at the whole point of it, is if I give you a value of x, you should be able to produce the value of y using this equation relationship. In which case, if I know that the value of x is 20, and really, I don't care what you call it, we're looking for the value of y here, right? So y is going to be 3/4 times 20, right? Which gives me 3 times 5, and that's 15. So the k value, if this point lies on this line, must be 15. Now, kind of the point of this exercise, by the way, because this is rather long, is the idea that we want to feel confident that if we have a line that goes through the origin, right, and passes through some point like 4, 3, then we know that it must have the equation y equals m times x, where m is the slope of the line. And the reason it has that is because of similar triangles. In this case, similar right triangles, in fact. And again, it doesn't matter. This thing, I could have taken this thing and drawn the x comma y one down here, or it could be absolutely monstrous. But either way, similar triangles then justify the fact that lines have these constant slopes, these constant rise and these constant, increases in x, increase in y, increase in x, increase in y. All right, let's kind of wrap it all up. So today we pushed it a little bit further in terms of equations of lines and their graphs. We introduced this idea of slope, right? Now you had seen it in previous lessons, and in fact, you've actually been seeing it, believe it or not, since sixth grade, right? The constant of proportionality is the slope. It's just another name for it, and especially when the slope is written in that fraction form, we can then use the slope to help us think about and understand why the graph of a line behaves the way it does. Especially written in fraction form, the denominator of the slope represents the increase in x, and the numerator of the slope represents the increase in y. Now, in follow-up lessons, we're going to start to look at slopes that are negative, right? And we're going to start to look at lines that don't just pass through the origin. And it's going to be an easy transition as long as you feel comfortable with what we're doing right now. So make sure to really hit that homework hard. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.